Hello, guys. A very good morning to all of you. Myself, Dr. Sunil Kumar, Assistant Professor, Department of Chemistry. Today's lecture is based on a special topic we call coordination chemistry. And what is coordination chemistry and what sorts of metals and ligands they are interacted to each other to form a special type of compound known as complex compound. Here we will discuss all the aspects related to coordination chemistry. So once we talk on the coordination chemistry, then first think that what is coordination? What is coordination? So coordination is nothing but formation of a bond between a metal and ligand, right? So suppose we have a metal. So this metal contains actually orbitals. So if it has a proper symmetry and energy, so it can be partially shown by this structure. So this is actually vacant orbital and it has tendency to accept electron pairs. Okay. So this is vacant, right? So here if we have another molecule called ligand, so that will act as a guest molecule, right? So this metal is called host molecule and L is called guest molecule. So the overlapping takes place like that. So this is M and this is M and like that. So this is L. So if this L act as a ligand, so it has a pair of electron, right? So this pair of electron containing orbital will overlap with metal orbital to form a bond called coordinate covalent bond. It means, so if M contains vacant orbital, so this is the notation of metal ligand bond. So it is called coordinate covalent bond, coordinate covalent bond. And in more general, it is also called dative bond. So here is pair of electron from the ligand orbital is donated to the vacant orbital of metal. So form a special type of bond is called dative bond. Okay. So let us consider here one example. Suppose we have one example that is K4 FeCN6, right? So this is the structure, chemical structure featuring different uh, elemental centers. Suppose here K4 that is potassium and in the square bracket there is metal iron and this is Cn that is cyanide ion. So here this structure comprised of K plus Fe2 plus and Cn minus. So these are the three species that actually accommodate to each other to form a chemical structure like that. So this is the complex compound. This is the example of complex compound. Okay, and the left side of the square bracket. So this is actually ionizable counter ion. Ionizable counter ion, right? And in the square bracket, so it is called coordination sphere, right? So this is coordination sphere. So the coordination sphere means there is a metal which is surrounded by the group or number of donor centers is called ligands. So in the square bracket there is metal and ligand. Okay, so this is called complex ion. Now in the next page, so this K4 FeCN6, right? So once it is dissolved in water, right? So this is partially ionizes 4K plus aqueous plus FeCN6 4 minus, right? So here you can see that once this complex compound is dissolved in water, so there is a dissociation takes place, and dissociation look like that. That is 4K plus aqueous and FeCN6 overall 4 negative charge. So this is complex ion. This is called complex ion, right? So this is counter ion. Counter ion here is potassium as a positive charge. So here total number of ionizable ions 4K plus and 1 FeCN6 for negative charge. So this complex ion actually does not show any characteristics taste of iron. Here iron exists as +2 state and cyanide as Cn minus. So in the solution phase, this complex ion does not show a characteristic property of Fe2 plus or Cn minus. So it means this complex ion has a tendency to retain its identity in the solid state as well as in the solution state. Okay, so this is the beauty of this complex ion, and this complex ion is actually negatively charged species here, and that is balanced by the counter cation 4K plus. So 4 positive charge, ultimately 4 negative charge, they will electrostatically interact to each other to form a solid compound. Okay, so how this coordination compound or complex compound is actually different from normal compound. Normal compound means, suppose we have a normal compound. So normal compound, let us consider sodium chloride, right? So this is salt and this is a normal compound, and this normal compound, when it is dissolved in water, so water is a polar solvent, so it has positive dipole as well as negative dipole. So once this sodium chloride is dissolved in water, so this Na plus aqueous and Cl minus aqueous. So after the dissolution of sodium chloride in the water, so it furnishes sodium plus aqueous and Cl minus aqueous. So here water molecule stabilizes in the solution to each ions through the dipole interactions. So Na plus is stabilized by negative end of the water, and Cl minus is stabilized by positive end of the water. So here all the ions remain in solution phase and gives the characteristics taste and property of these ions. Okay, so but this complex ion does not give any taste of Fe2 plus or Cn minus. So this is the different, and this compound actually loses its identity in the solution phase. So because of presence of this sodium plus and Cl minus in the hydrated phase, but in the solution phase it does not actually exist as Fe aqueous and Cn minus aqueous. So this is that is why it has a unique property, and like color, or you can say simply optical properties like color, magnetic properties, either it may be paramagnetic or diamagnetic, and special applications. Okay, so in the nature you can also think that that is hemoglobin, which will act as a oxygen transport, right? So this hemoglobin is actually complex compound, and the hemoglobin, once you talk hemoglobin, that is globin, right? So this is the iron porphyrin complex. So this is iron porphyrin complex, right? And chlorophyll. So chlorophyll. So because of that chlorophyll, all the green, all the plants appears green color, and that is used to create photosynthesis in the green plant. Okay, so this is also magnesium porphyrin complex. So in the nature, in the biological science also, you can think that this hemoglobin and chlorophyll is a complex compound having a different and specific chemical structure. So by inspiring the natural complex compound, we can move towards modern chemical structure and complex compound, and variety of coordination compounds can be created. Okay, so here one most important example, like double salt, that is potash alum. So K2SO4 Al2SO4 whole thrice into 24 H2O. So here this actually chemical structure is called double salt because of presence of two salt, that is potassium sulfate and aluminum sulfate, and they are stabilized by water of crystallization. Here water of crystallization is 24 H2O molecule. So these 24 H2O molecule stabilize these two salts in the solid state. But once this is dissolved in polar water molecule, so what happens here? All the salts which contains positive and negative charge in the solution phase, so this is K plus and SO4 2 minus and Al 3 plus. So all these species in the aqueous phase, right? So either it is normal salt or double salt. So once it is dissolved in the water, so they get dissociated and furnishing corresponding ions, either cations or anions. So this these ions actually gives characteristic taste and property by suitable reagents. So either normal salt or double salt, both loses its identity in the solution phase, but complex ion does not loses its identity in the solution state. So that is why complex compounds are actually unique compared to normal salt or double salt. So what happens here? We can also give, suppose NiCl2. So this is nickel chloride. In the solid state, it looks greenish. So once it is dissolved in water, right? So what happens? So this is NiH2O whole 6, right? This is overall 2 positive charge. And if we add ammonia, right? So what happens? NiNH3 whole 6 2 plus. In the solid state, pale green color, right? but once it is dissolved in water, it is deep green color. Deep green color. Here it is pale green color, right? So what happens? This is a normal salt, nickel chloride. Once it is dissolved in water, it is getting the structure like that, Ni, and that is coordinated by water molecule overall 2 positive charge. Its color changes from pale green to deep, deep green, and in this actually compound, if you add the ammonia in the liquid phase, what happens? This water molecule is replaced by the ammonia, and ammonia molecule enters to the coordination sphere. This is the structure Ni NH3 ka whole 6 overall 2 plus. Now this compound show very good blue color, right? Blue color. So what happens here? Here this is chloride, and there Cl minus. Here it is H2O, and here it is NH3. So the role of these three species is different with respect to a nickel metal. So here chloride ion has actually different capacity to change the color of nickel. Here H2O molecule that can change the color slightly to the nickel, and here ammonia molecule, so that completely change the color of this nickel in the complex. So complex compound has different colors, and that is why it is used in different perspectives and application in the nature. Okay, so what happens next? Now suppose we have a complex compound like that. So this is actually CO and H3 whole 6, right? And this is, you can say that Cl3, right? So the counter ion may be either left side of the bracket or right side of the bracket. So here the counter ion, that is chlorine. So how actually it exists? CO and H3 whole 6. So this is 3 plus, and this is 3Cl minus. So because of presence of electrostatic positive charge on the complex ion, so this is complex ion which contains 3 positive charge, and H chlorine contains 1 negative charge. So overall 3 chlorine, 3 negative charge. So 3 positive charge and 3 negative charge, they are balanced to each other, right? So this is complex ion, and this is actually positive complex ion. So this is positive complex ion, and this is stabilized by negative counter ions, right? So this is what. So this complex ion may be either positively charged or negatively charged. So complex ion may be either positively charged or negatively charged. Negatively charged, right? So this is the actually beauty of this type of coordination compound or complex compound. Okay, so what truly matters here, once we consider any complex, that is M, and suppose this is Ml6, or this is N plus, right, or N minus, or it may be N minus. So this is the general formula of a complex compound Ml6, and overall charge it may be N plus or N minus, depends on the presence of counter ions. So how this is different structure? So this depends on metal. Metal, it is either 3D, 4D or 5D. Okay. And what is the oxidation state of this metal? Oxidation state of this metal, right? And another important parameters is ligand. Ligand. So ligand, either it is monodentate ligand, monodentate or bidentate, or polydentate, or polydentate. Okay, this may be chelating, right? So the behavior and characteristics of the complex ion will solely depends on the nature of the metal in the coordination sphere. So the variation of 3D to 4D to 5D, right? So the different characteristics and properties can be obtained, and a particular oxidation state. Okay, and this 3D, 4D, 5D means we are talking transition series. Okay, so transition metals actually found in the 3D series, 4D series and 5D series. Okay, so what happens here? 3D series, d orbitals. So d orbitals actually d orbitals are actually suitable and proper for the formation of the coordinate covalent bond. So because of proper symmetry, energy and compatibility with the ligands, these d orbitals are suitable. And because of the diffuse, it is actually diffusion and extensions of the orbitals, they can overlap the orbital of ligand. Okay, so to form a dative bond. So these d orbitals are classified as dxy, dyz, dzx, dx square minus dy square and dz square. So there are 5 d orbitals which have different spatial arrangement and orientations, so that occupy the orbital of ligands. Okay, so how these different orbital look likes and how it forms a complex with different ligands, that will be discussed. Okay, so dxy. Now first see what do you mean by dxy. So this is x-axis and this is y-axis. And now if the d orbital look like that, right? So here this is plus and here plus, this is minus and this is minus. So these orbitals are 4 lobes, right? So this is xy, and the orbitals actually exist in between the x-axis and y-axis. So in between the axis ligand, this is dxy, right? And similarly dyz, this is y and z. So this is looking like that. The shape of each d orbital is dumbbell, right? So this is dzx, this is z and x. So this look like that. So these are the 3 set of orbitals called dxy, dyz and dzx, and all these orbitals exist in between the axis, and rest of the 2 orbitals, so that is dx square minus y square and dz square. So this is existing as like that. So dx square minus y square, this is x and y. So this is axially oriented, right? So it will just lie on the x-axis and y-axis. So this is dx square minus y square, right? And next, this is dz square. So what happens? So this is, suppose z-axis, so z positive and z negative. So like that. So this is surrounded by a ring. So this is dz square, right? So d orbitals had three different sets of orbitals and two different sets of orbitals. So all these orbitals have different tendency to form a dative bond with a shared pair of electron which are present in the ligand. So this is the actually overview of the orbitals, so that can accommodate a pair of electrons from the ligand. Okay, so next, how these metal orbitals and actually form complex with the orbital of the ligand. So d orbitals actually extends especially and diffuse towards the capture of the orbitals of the ligands. So but rest of the like s and p block, s orbital and p orbitals, so have higher energy and less symmetry, so it does not accommodate the orbital of ligands, so it will not give the stable complexes. But the d orbitals, all the d orbitals actually stabilized by the orbital of ligands, and these ligands actually stabilize the metal orbitals and give a characteristics complex compound. So the complex compound actually that was actually discovered by a foreign scientist, chemist, that is Alfred Werner in 1893. Alfred Werner, so is a scientist who have studies deeply about the chemistry of metal and ligand, and on the basis of actually chemistry and type of interactions, they have discussed and rationalized various aspects. So this is the way we can consider and how this Alfred Burners have developed the coordination chemistry. So that will be discussed later in the next lecture. Okay, thank you.